Okay, welcome to session 2 of surfactant chemistry. Obviously in session 1 we learned a bit about surfactants. So we said they have a head. I'll just make sure I can actually write on this slide. We have a head group and we have a tail. And we learned something about the chemistry of the head groups and something about the tails. And we basically said that depending on the head group depends on the kind of things that you can do with it. And there's various parameters you can calculate. For example, you can calculate the HLB if you've got a non-ionic surfactant. Okay. So we covered quite a lot of definitions. What I wanted to move on today was to talk more about the absorption at interfaces. This is a key property of surfactants, is their ability to form an oriented monolayer at the interface. And as you can see here, we've got an oriented monolayer starting to be formed. And we're going to talk about why they do that. And we're going to talk something of the implications of what happens when they do that as well. Okay, because this process here is actually quite crucial in a number of fields. Okay. So before we get going with talking about surfactants, we need to sort of talk a little bit more about the properties of these air-water interfaces in the first place. And it's probably something you've heard and you've certainly seen examples of, which is that at the air-water interface there is an interfacial tension. Okay, and this interfacial tension, for example, manifests itself in the meniscus that you get at that interface. Okay, so I've got an analogy for why that's actually happening, and that's what's written in front of me, which is basically the idea of having two groups of people within a party who just really don't get on very well. And so let's just think about that. If you have a person who's standing here in group A, they're pretty happy because they're surrounded by loads of other people who they like and who they can talk to. However, if you move to this point here, more at the interface of group A and very close to group B, then you have a situation where this person has a few people around them that they're happy to talk to and they like, but equally they also have some people around them who they don't like. And so this person here is more uncomfortable than this person standing here, and therefore the person standing here at the interface is basically experiencing a higher level of stress or a higher level of tension than the person here. But of course they have to stay here because there's no room for them in here. And likewise, you've got the same scenario in group B. Someone standing here is fine, but someone stands here, they're less happy. And of course, if this person tries to move here, then they just make a new person. They put a new person here. So you've always got to have people standing at these interfaces. Okay, so that's the analogy. Let's think about that in terms of molecules. Okay, and it's basically the same idea. Okay, so if you've got a water molecule, so you've got a water molecule here, you have plenty of favorable bonding interactions with other molecules around it. Okay, so plenty of favorable bonding interactions. This molecule is pretty happy in terms of its position in life. Molecule B, on the other hand, has only got a few, or fewer anyway, favorable bonding interactions around it, and it's got an awful lot of stuff that it cannot easily bond with up here. All right, so because of that, molecule B doesn't get the same level of favorable bonding interactions, and therefore molecule B is in a higher energy state than molecule A. Okay, now of course molecule B would tend to prefer to reduce its energy, and so it's going to try and pull itself back into the bulk. But of course, if it does that, then another molecule has to take its place. And so, there then becomes an effective tension at that interface that kind of holds it in place. So, this is the interfacial tension, basically. That means that always there is going to be molecules at the interface, and this interfacial tension is effectively counteracting the net inward pull, the tendency for B to want to come and become A in order to reduce its energy. Okay, and this interfacial tension forms this kind of skin-like layer at the interface, and obviously in water's case, the air-water interfacial tension is pretty high, and so you get the meniscus forming. And so this whole concept is basically saying that there is work that needs to be done in order to put a molecule from the position A to position B. And that work that's required to be done is given as the, this is here, the work required to be done is the area that you need to make of the interface multiplied by the surface tension. And so, for this reason, if you make this smaller, then the work done is less. And that has implications in terms of droplet shape and other things. But anyway, this here is the surface tension. Okay, so this is the surface tension. Also known as the interfacial tension. Surface tends to refer to solids, solid air, solid liquid. Interface tends to refer to air liquid or liquid liquid, just as an aside. But we can call them either. And I will use the phrase interchangeably, interfacial and surface tension during this lecture course. Okay, but basically this is a pretty simple equation, and it basically says that the bigger the surface tension is, the more work that's required to do it, and equally, the bigger the area is, the more work is required. Okay, what are the implications of this? Well, implications are pretty clear. So, for example, if you have droplets of water, they would tend to be spherical, and that's because spherical droplets have a smaller surface area to volume ratio than any other shapes, and so therefore you're reducing the work that's required to be done to form these things. Equally, there are plenty of animals that rely on surface tension in order to even be able to survive. And so, for example, water boatmen wouldn't be able to swim on water if surface tension was lower than it is. Salad dressing separates. Why does it separate? It's because the oil-water interfacial tension is high. You know that because you know that those two things don't mix. Okay, and what happens is, in order to reduce the work required, the salad dressing separates. So now we just have the interfacial area is just this disc here that I'm kind of highlighting. Otherwise, the interfacial area would be much higher if you had loads of little droplets, each with their own interfaces. Okay, and finally, and this is kind of a fun example, you can watch these videos of this astronaut who was basically doing a whole bunch of experiments in space. And one of the things he did was he took a wet towel and he basically wrung it out. Now we know what would happen on Earth. The water would just drip straight off the towel down and it would make a bit of a flood. What happened in space is, because of the interfacial tension of water, the water just stayed around the towel and it stayed around his hands and just flowed away down his arms, basically. That's kind of an interesting thing, and it shows that the surface tension is stronger than the gravity, than the effect of gravity when you have very little or pretty much zero gravity.